So the moments that we talked about when we were looking at center of mass, those are first moments. And so in particular, when I say that, I mean that we're looking at the integral of the first power of x with respect to the density dx. There's also second moments and third moments and so on and so forth. And now we're going to look at moments of inertia, which are second moments of a certain type. And so here's a touchy-feely definition for you. It's not precise in terms of formulas, but whatever. The moment of inertia about an axis is the amount of torque needed to generate angular momentum about that axis, right? So what exactly does that mean? And by the way, if you're wondering why the heck do they call it moment of inertia, it's the same root as momentum. It has nothing to do with time. So what does this mean? Well, the idea is that if you have a larger moment, then that corresponds to it being harder to change momentum. And so if you, just from your personal experience, consider that you have like, say, like a hollow tube of PVC pipe, right, of some length, yeah? And actually we'll take two of these and copy it, paste it, boom, here's my other one. Now in the first one, I'm gonna take some lead weights and I'm gonna put them out here on the ends so that they're distributed as far as possible from the center. So imagine this is the center and you're like gonna be grabbing it, you know, around, oh, I guess your finger better be longer. Okay, so this is going to be where you grab it, right? As opposed to if we put them right here in the middle, and then we grab it in the same place. So we're going to grab it right here. Now, if you try and spin these, which one is going to spin more easily? Well, definitely this one is going to be easier, right? Because the weights are kind of right under your hand. This one over here, you can imagine in order to rotate that, you've got to have kind of like, there's the torque that this is exerting at some fair distance, right? It's going to be a lot harder to spin. That's the idea. Now, in a three-dimensional context, we're going to be thinking of, like, suppose you've got a vertical plane that's bisecting your mass. Here's our potato, and we're going to be checking out the moment of inertia of the potato. So now instead of thinking about like twisting the potato this way or this way, so on the X or the Y axes to try and spin it, X or Z, we want to instead think about what happens if we rotate it about this axis that's puncturing through the plane perpendicularly. Okay, and then the formula for these are, let's see, so if we're taking the x-axis as our axis of rotation, then it's going to be the triple integral over E of, and then we take the other two variables, y and z. And now these are both squared because, like I said, this is a second moment. And then we've got the density. And then we've got our volume element. And it's often nice to set up these rotational things in terms of polar. So if this one were done in terms of polar, then you might set it up with, say, the triple integral over E, and then you'd have r squared times the density times r dr dx d theta. So we would be doing polar, well, actually cylindrical, I guess, using the x-axis as the Cartesian one. And then let's see, so the moment of inertia about the y-axis is going to be the same setup, but now since we're doing y, we have the other two variables x and z showing up in our integrand. And the z moment, x squared plus y squared times the density with respect to volume. Okay, and so a key thing that's interesting about the moment of inertia is that it determines the amount that a material will bend. So like how much it will deflect under force. And so a higher moment of inertia is going to result in like a more rigid, less bendy type of object. And so you can say, okay, so how do we make, say, a beam that is as straight as and non-bendy as possible? Well, it turns out that instead of taking something that has a solid cross-section like this, you're going to be much better off taking something that has a hollow cross-section like maybe this, so that the mass is spread out at a further distance from the middle. And so you may have noticed that if you have a cylindrical rod, it's actually going to be more impervious to bending than if you have a solid core rod. And now the only problem is in terms of like building and stuff like that, it's not so nice to use these round ones because they don't connect to each other for, you know, making walls and so on and so forth, and they can roll away and whatever else. But when it comes to things like that, people came up with a good solution for how, you know, what kind of a cross section keeps the mass away from the center as much as possible. And it's something that looks like this one. And so this is what you've seen on those girders and high-rise apartment buildings and whatever else, the skeletal framework that they make. This is the I-beam, although it looks a lot more like an H if you look at it sideways. And so one of the reasons for using this form right here is that it has a very high moment of inertia.